Hey everyone, welcome back to another physics past paper video. Today we're going to talk about the May-June 2024 paper 1, variant 1-2. So let's start with the paper. What is a scalar quantity? So we know scalar quantities are those that are only represented by their magnitude. So no direction. So a quantity that can be represented as two perpendicular vectors, no. Quantity that does not require a unit, all quantities require a unit. Quantity without a direction, that is the correct one. The value of quantity x has a percentage uncertainty of 2%. Value of quantity y has a percentage uncertainty of 4%. Value of quantity w is calculated from the values of x and y. Value of w has a percentage uncertainty of 8%. What could be the relationship between w, x, and y? Okay, so percentage uncertainty in w is coming from some of, like I'm talking about some kind of sum of percentage uncertainty of x plus some kind of uncertainty, percent uncertainty of y. But we don't know what are the values of coefficients over here are. We know that the sum is the 8%. So we have 2 over here, 2%, and this is 4. So blank, blank. So we know how to make up a sum of 4 basically. So there is only one particular way to do that. We multiply this by 2 and this by 1. There is no other way to do this. So this means that x is squared somewhere. So either it's x squared y, x squared over y, or y over x squared. If you swap the places, this would become 10 instead. So this would not be correct. This would add up to just 6%, also the same. This would become 10. This is becoming 8%. And this is one of the options. Football is kicked so that it moves vertically upwards through the air. What is the variation in the air resistance and the resultant force acting on the ball as it moves vertically upwards? Okay, so remember one thing. This is the ball. Its weight is acting downwards and the ball is moving upwards. So obviously that means that the resistance is also acting downwards. Basically we can actually add it like this over here. So the resultant force would be R plus W. Now the object is decelerating upwards. So object is decelerating upwards because the acceleration of due to gravity is acts downwards. Speed decreases. We know that the air resistance will decrease as the speed decreases. With speed will decrease as speed decreases. So air resistance decreases. That means these two options go right away. If the air resistance decreases, resultant force, which is the sum of R and W, would decrease. Resultant force, which is the sum of R plus W, would decrease consequently. So A would be correct. Right. Which statement is not correct? Acceleration can be determined from gradient of the velocity time graph. That is actually correct. Acceleration is the rate of change of velocity. Displacement can be determined from the area under the velocity time graph. So 3 out of 4 are not the right answer. So that means fourth would be velocity is the rate of change of distance. That is incorrect because it's the rate of change of displacement. The diagram shows a laboratory experiment in which a feather falls from the rest in a long evacuated vertical tube of length L. Feather takes time t to fall from the top to the bottom of the tube. How far does the feather fall from the top of the tube in half the time? Okay, so since the initial velocity is 0 because it's falling from rest, you have s is equal to half g t squared. So when you take the total s, L, would be half g t squared. Now we want to find out what would be at 0.5 t squared. So what we do, half g would remain the same. L prime, the distance, new distance, is what we need to find out. So what we can do is we can take a ratio of these. So L prime, L, this would be half g 0.5 t whole squared ratio half g t squared. So half g would cancel out, t squared would also cancel out. So we are left with 0.5 squared ratio 1, which is 0.25 ratio 1, which means that L prime over L is 0.25. In short, that means the new L would be 0.25 times by L, which is going to be B. Simple mathematics over here, nothing complicated. A car travels along a straight horizontal road. The graph shows the variation of the velocity v of the car with time t for 6 seconds. The brakes of the car are applied from t is equal to 1 second to 4 seconds. How far does the car travel while the brakes are applied? Okay, so while the brakes are applied are between 1 and 4. So the area under the graph basically will tell us the answer. So all we need to do is to find out the area under the graph. S is equal to half sum of parallel sides, which is, wait a second, this is 8, this is 22, so 22 plus 8, which is 30, times by this. So 30 times by 3, 2, 15, and that would be 45. Simple mathematics over here as before. Two satellites in deep space collide inelastically. That means kinetic energy not conserved. Sorry. What happens to the total kinetic energy and total momentum? So total momentum is conserved, kinetic energy not conserved. So total kinetic energy reduced, total momentum reserved. So process of elimination, simple, straightforward. What is a reasonable estimate of the momentum of a family car traveling at 25 kilometers per hour? Right. So family car, let's say it weighs about 1,000 kg between and 1,500 kgs. It's traveling at 25 kilometers per hour. So we need to convert it into speed. So this would be 25 times by 1,000 over 3,600. So 10 over 36, so 250 over 36, 6.944. So it's meters per second. So MV, which is the momentum, it could be in between 6944, which is roughly 7,000, you could say, and 1500, sorry, 10,000 roughly. So 10,4016. So roughly between 7,000 to 10,000. So that would be 10 raised to power 4. Yes, that we are correct. All right, so let's move forward. A ball collides with a wall. Before collision, the ball moves with a velocity of 8 meters per second to the right. After the collision, it moves with velocity 3 meters per second to the left. So this is the wall. This is the initial velocity, 8 meters per second. And this is the final velocity, 3 meters to the left. What is the change in velocity of the ball during the collision? So change in velocity is going to be v minus u, but u is in already other direction. So basically this is v minus u. So this is 3 minus 8. This is 11. And the change is actually happening towards the left side. So it's towards the left. So if the change in velocity is happening to the left, change in momentum would happen towards the left, and force experienced by the ball would also be to the left. So the direction of change in velocity change in momentum, the force on the object by the ball, and if there's a change in velocity, there's an acceleration also. So they're all going to be same direction. So the ball is accelerating to the left, it's experiencing a force to the left, etc. A lead pellet is shot vertically upwards into a clay block that is stationary at the moment of impact, but is able to rise freely after impact. Okay, so we have the diagram. Lead pellet is 5 grams, stationary clay block mass is 95 grams, impact velocity 200 meters per second. Okay, so it embeds itself in the block and does not emerge. So after the collision, the masses will add. How high above its initial position will the block rise? Okay, so basically we need to find out what's the final velocity after the collision. So we basically need to figure this out. So we have m1 u1 plus m2 u2 equals to m1 v1 plus m2 v2. This is just conservation of momentum principle. Mass before is 5 grams. So 0.005 times by 200. And the second block is stationary, so 0. Now their masses are combined, so 100 grams, 0.1. Yeah. Right. And then times by velocity, which we need to figure out. So 5 times by 200, divided by 1000 and divided by 0.1. So 10. Right, okay, so this is the initial velocity that the complete 100 grams mass starts to go upward. So we need to go how high above its initial position. So initial velocity is now 10 at the highest point v would become 0, so we can use 2as v squared minus u squared, so 2 times by minus 9.81 times by s 0 minus 10 squared. So minus minus will cancel out, so this would be 100 divided by 2 times by 9.81. So this would be 100 divided by 2 divided by 9.81. So this is 5.096. So this one. That's it. Sorry. Two forces act on an object. Which diagram represents a couple? So couple, two forces acting in different directions, but they need to be separated and separated by some distance, by a distance. Right. So these two acting in the same directions, no. They are acting in opposite directions and they are separated by some distance. So this is the correct one. They are also acting in the same direction. So, and these are also, they may be acting in opposite directions, but they are different forces. So these two same magnitude forces are identical forces acting in different directions, opposite directions, you could say. Right. Okay. The diagram shows a uniform rod XY that is freely hinged to a vertical wall at end Y. The rod is at an angle 60 degrees to the horizontal. This hinged beam type case comes up very frequently. So this is one of the frequently examined questions. And if it's in equilibrium, it will obey the triangular forces rule. The directions will be a closed loop. Force F acts at an angle 30 degrees to the rod at end X. The rod has weight 3 Newton and is in equilibrium. What is the magnitude of the force F? Okay, so if it is in equilibrium, that means moment about this hinge about point Y would be the same. So we need this distance, perpendicular distance, from the line of action of force. So this would be 3 times by, oh right, so if xy is L, that means this length is L, so that means half of that would be L over 2. So at 3 times by L over 2, we need the perpendicular distance, so 3 times by L over 2, sine of 60. Minus, because this is clockwise, anti-clockwise, now we need the anti-clockwise. So what we can do now, what if we make this force, resolve it this way? So this would be 60, so this would become F cos of 60. So this would become F cos of 60 times by complete L, because now the distance is just L. And this is all equal to 0. So, right. Sine of 60 is under root 3 by 2. Cos of 60 is 1 by 2. So you have 3 over 2 times by root 3 over 2 equals to, by taking everything on the other side, so F cos of 60, 1 over 2, and L gets cancelled on both sides. Right, so this 2 can cancelled also, so this is 3 under root 3 over 2. So you have 3 root 3 divided by 2, so this is 2.598. This is going to be C. Right. Water has a density of 1 gram per centimeter. Glycerin has the density of 1.3 grams per centimeter cube. A student measures out the volume of 40 centimeter cube of glycerine into a container. The student adds water to the container to make a mixture of water and glycerin. Assume that the total volume of water and glycerin does not change when the two liquids are mixed. Which volume of water needs to be added to make the mixture of density 1.1? Okay, so the total density is this. We are adding some mass of glycerin, some mass of water. Right, okay, so let's solve it this way. This is also an important recurring question that often flummoxes the students. So we need the density, right? So we need the total density. Total density is going to be the total mass over total volume. So total mass is density times by volume. We don't know that. Density times by volume of water. We don't know that. Plus density times by 40 centimeter cubed divided by total volume, which is going to be 40 centimeter cubed plus volume of water. And now the total density is coming out to be 1.1. So now we just need to solve this. VW plus 1.3 times by 40, so this is 52. And then 1.1 times by 4t, so this would be 44 plus 1.1 VW. So this goes on the other side, so 1.1 minus 1 VW, 52 minus 44. So VW times by 0.1, and this is going to be 8. So VW 8 divided by 0.1. So this is going to be 80 centimeter cubed. Let's go through. Yeah, right. So basically total mass over total volume, centimeter cubed. We just rearranged, did some algebra. So this is going to be that. This is total mass over total volume. Right. Okay, moving on. The force resisting the motion of a car is proportional to the square of the car's speed. The magnitude of the force at a speed of 220 meters per second is 800 newtons. This we are talking about the force resisting the motion. What is the useful power? What useful power is required from the car's engine to maintain a steady speed of 40 meters per second? So, okay, useful power output. So, okay, so power is force times by V. We need the magnitude of the force at a speed of, wait, oh, sorry, the key is actually written over here. Sorry, my bad. Force is proportional to V squared. So basically F1 equals to V1 squared over F2 over V2 squared. It could be the other way around also. It could be 2, 1, 2, and 1. Right. Okay, so this is right. Okay. Now what do we need? If at 20 it is, we need 40 meters per second. Earlier was 20 meters per second, and this is 800. So now the speed would be 1600 divided by 400 times by 800. The force would be 3200. Right. To maintain a steady speed, so that means there is no net force, no resultant force is zero. So power would be 3200 times by, so the driving force would also be the same, times by this. So this times by 40, so this would be 128 kilowatts. 14 would be C. Right. A box of weight W is pulled by a force P along the slope. Length of the slope is D and the box rises a height h. The frictional force between the box and the slope is F. The diagram shows the direction of forces. The purpose of the slope is to raise the box vertically. Which expression gives the efficiency of the slope? So we know efficiency is useful power output or useful output, whatever this is. It could be work and input, total input, whether it's work or that power, either way. So the purpose of the slope is to raise the box vertically. So the useful output work is basically the change in potential energy, so MGH. So WH is the useful output work. Input work is actually coming from P. So P times by distance t. So no, this is going to be correct. The kinetic energy of the particle is increased by a factor of 4. By what factor does its speed increase? So this is clearly 2 because EK is proportional to square of V. So if we increase it by 2, this increases by 4, basically, factor of 4. So basically 4V. A mass of 28 grams is raised vertically upwards through a distance of 4.6 meters. What is the change in gravitational potential energy of the mass? So this would be C joules, we need kgs. So 28 grams divided by 1000 times by 4.6. So 2.8 times by 4.6 divided by 1000. So this is 0.01288. So that is sorry, this is 28. My bad. 0.128. So this is going to be 1.3. A sample of the metal is subjected to a force which increases to a maximum value and then decreases back to 0. A force extension graph for the sample is shown. When the sample contracts, it follows the same force extension curve as when it was being stretched. So basically that's a feature of elasticity. What is the behavior of the metal between X and Y? So first off, it remains elastic because even wait a second. Yeah, so even from this point, it goes back to the same point, right? It goes back to the same, following the same curve, so it remains elastic. So elastic but not plastic. This is the only thing because there is no plastic deformation once the force on the object is released. Two wires, P and Q, are made of the same material, are stretched with an increasing force. The graph is plotted of the variation of the force of the extension of each wire. The wires have the same original length but different diameters. What is the ratio diameter of wire Q, wire P? Okay. Made of the same material means Young modulus is the same. but different diameters means different cross-sectional areas from stress force over area. So stress is force over area, strain is extension over the original length are the same. Stress over strain is your E, that's going to be the same for both of them. So we need to equate Young modulus for both of them. So we need an expression for both of them first. So E1 is equal to force over area, right. So total extension is different. Right, okay. So wire this one, let's give, oh sorry, wire P, sorry. So you have force 2 AP divided by x over L, or you can do it this way to save some space. X over L extension is 3 millimeters, which is 0.003 divided by the original length L. They have the same L, so we don't need to worry about that. So this would actually become 2 over AP times by L over 0.003. Now, Young modulus for Q, this would be force is 2 again, and a Q divided by extension is now 0.001 because 1 divided by 1000 and the original L. So this is 2 over AP, AQ times by L over 0.001. All right, now EP is equal to AEQ. So 2 over AP times by L over 0.003, 2 over AQ, L over 0.001. So right off the bat, 2L get cancelled. So the area ratio, what we get, this goes on this side and this is Q. This is going to be 0.001 over 0.003, which is basically just 1 over 3. And area, that is pi d squared over 4. This would just simplify to dp squared over dq squared 1 over 3. Oh, right, so the diameter of wire Q and diameter of wire P just the other way around, and then the square root, this would be square root of 3. This would be C. So a little mathematics required. Right. The extension force graph for a spring is shown. What is the spring constant of this spring? Okay. So extension is shown in centimeters, so we have to be careful. So extension is 15 centimeters, so this is going to be 0.15 meters. Force is given as 6 newtons. So spring constant would be 6 over 0.15. Remember, if this were the gradient is the reciprocal of 1 over k, because it's change in extension over change in force. So that's the reciprocal of the spring constant. So it's not 15 over, it's not 0.15 over 6, it's 6 over 0.15. So 40. So 40. A man stands stationary in front of a swing. A child sits and swings. The child blows a whistle that emits a sound at constant frequency. The man observes the frequency of the sound when the swing is at x, y, z. When will the man hear the highest frequency? So when it's going from this thing. Actually, no. Wait. Speed, we know from simple harmonic motion that this is where the speed would be the highest. So when it's at y moving towards x. So yes, C. Yes. So pendulum motion, this is where the mean position is where the speed is the highest. A loudspeaker is playing music in a room. The door to the room is open and has a width of this. Sound waves of different frequencies pass through the doorway and diffract. Speed of the sound in air is this. What is the frequency of the sound wave? Which frequency of sound wave diffracts most as it passes through the doorway? Okay, so one thing you have to remember, diffraction diffraction becomes more significant when the aperture is approximately the same order as the wavelength. So aperture is 0.8. So we need the frequency. So frequency is V over lambda. Sorry, V over lambda. So V is 340, lambda is 0.8. So let's see which frequency comes closest. Divided by 0.8. This is 425. This would be D. A stationary sound wave is set up between a loudspeaker and a wall. The microphone is connected to the cathode ray oscilloscope and is moved along the line directly between the loudspeaker and the wall. The amplitude of the trace on the CRO rises to a maximum at a position X and falls to a minimum and then rises once again to a maximum at position Y. So, wait a second. The amplitude of the trace, this is the antinode, this is the antinode, and this is the node somewhere in between. Okay. The distance between X and Y is 33 centimeter, right? Speed of the sound is this. Which diagram could represent the CRO trace of the sound received at X? Okay, so we need the time period. Okay, so remember this, that antinode to antinode distance is lambda by 2, just like node to node distance is lambda by 2. So lambda would be 2 times by 33 centimeter, which is 33 divided by 100. We need to first do it in meters, divided by 100. So this is 0.66 meters. We need to find the time period now. Time period is lambda over V. Right? So because like V is equal to F lambda, so this is 1 over T lambda. So you can rearrange that however you want. So lambda over V. So lambda is 0.66 meters, V is 330 meters per second, and that's why we need it in meters. So you get divided by 330, so 0.002 seconds. So this is 2 milliseconds. 2 milliseconds is the time period. Now, if we divide this by time base, we should be able to figure out how many grids this is going to be, how many centimeters this is going to be. So 2 divided by 0.5, so this is 4. 4 should be the time period. Yes, that's it. This is your time period, 4 centimeters. So B. Okay. Polarization is associated with certain waves, transverse waves. This is one of the distinguishing features between transverse and longitudinal waves. So which waves cannot be polarized? Longitudinal sound waves moving from a source, that's the only. All other waves are transverse. A guitar string is plucked. Which statement describes the resulting waves? The longitudinal waves on the string cause longitudinal waves in the air. No, on the string, those are transverse waves. So transverse waves on the string cause the longitudinal waves in the air. That is the only correct option. The diffraction grating with n lines per meter is used to diffract light of various wavelengths lambda. The diagram shows the relationship between diffraction angle theta and lambda for different wavelengths in nth order interference pattern. So we have n lambda d sine theta. So we have sine theta as the y and lambda, so you have sine theta is equal to n lambda over d. So n over d would be your gradient. So n over d, okay, and d is basically 1 over n. So n, sorry, no. N over d would be your n. So yeah, this one. A stationary sound wave is formed in the air column inside a tube that is open at both ends. So remember, at open ends we get antinode and antinode. Stationary wave has 3 nodes. How many antinodes does it have? Okay, so let's try to make that. So you have a node, antinode, node, antinode, node. We have 3 nodes inside, right? 3 nodes. So 1, 2, 3. So antinodes would be 1, 2, 3, 4. 4. Interference fringes of separation x are observed on a screen at a distance of 1 meters from the double slit that is illuminated by yellow light of wavelength this. At which distance from the double slit would interference fringes of the same separation x be observed when using blue light of wavelength? Okay, so we have x is equal to a lambda ax over d. So we need x, right? So x should be the same. X and a both are the same. So basically lambda d is constant, right? So if the same separation x and the same double slit basically, so lambda d is constant. So lambda 1 d1 equals to lambda 2 d2. First lambda 1 is 601 meters, and this is now 400 nanometers, and d2 we need to figure out. So d2 would be 6 by 4, 3 by 2, 1.5. Simple math over here, simple ratio math over here, nothing more. What is the definition of potential difference across a component? So work or energy per unit charge. So energy transferred per unit charge, energy transferred per unit current, simple A. The diagram shows the cell of a negligible internal resistance connected to a switch and 2 resistors of resistances R and 2R. The circuit also contains 2 ammeters X and Y. Reading on the X is for when the switch is open. What are the readings on X and Y when the switch is closed? Okay, so that means 4 amps. 4 amps. So remember one thing. If the current is only flowing through this path, V would be just simply IR. So that would be just 4R. So V is going to be the same thing over here. The EMF does not change. So let's call it EMF. EMF. Now the current is flowing through this path also. So this changes the effective resistance. So this would be 1 over R plus 1 over 2R. So 2 times by 1. So this is going to be 3 over 2R, leaving effective resistance to be 2R over 3. So now Ix going to be V over effective resistance, which is going to be EMF over effective resistance of 4R divided by 2R times by 3. So 2 times by 2, 2 times by 3, 6. So this is going to be 6 amperes. Now this is the total of that. We can find out the current in this, and we can find out the current in this easily now, because we know the potential difference across them also. So IY, potential difference is 4R divided by 2R. So this is going to be 2. Similarly, for IR, simply, we already know the answer to this, but just to be sure, 4R is the EMF or the potential difference divided by R. So this is 4, just to be clear. So this is 2 ampere, this is 4 ampere, totaling 6 ampere. So this would be C. The IV characteristics of 4 components A, B, C, D are shown. Which component has the greatest resistance when the potential difference across is greatest resistance when the potential difference across it is V. So greatest potential difference, greatest resistance. So remember one thing, V is equal to IR implies a straight line relationship, because this is the proportionality. Simply when we say V proportional to R, it implies a straight line passing through origin. Passing through origin. Like Y equals to mx. Y being the, let's say in this case, I over here, M would be V. X would be V, and this would be 1 over R. But this would only be for the straight lines A and B. So in the case of A and B, you could say that B would have a greater resistance. But for C and D, these are non-linear. So that means they are non-ohmic conductors. So non-ohmic conductors. So these are ohmic and the other two. So we cannot apply the same rule over here. So what we can just simply do is resistance is equal to I over V, smallest current value at the same V would give us the answer. So at V1, D has the smallest current, so D would be the right answer. A cylindrical wire has a cross-section area A and number density of the free electrons N. The wire has the current I and the free electrons have average drift speed V. Right? The second cylindrical wire has cross-sectional area of 0.5 A, the number density of free electrons 2N, and in the wire the free electrons have average drift speed 2. Okay, what is the current in the second wire? Right, okay. Right. So we have the formula I is equal to N A. QV or EV doesn't matter because we have free electrons over here. So we can take it this way. Cylindrical wire over here would imply that the area is pi d squared over 4. We don't know anything about, okay, they have given us, okay, all right. So let's say you have I1 ratio I2. Okay, we need to give it in terms of I. Okay, so let's see that. In the first one, you have free electrons N, A. Free electrons are and drift speed V. Okay. I2, you have 2n free electrons. Cross-sectional area is 0.5. E remains the same because we're talking about free electrons. And V is 2V. So 2 times by 2 times by 0.5, that is just 2. So 2, A, N, A, E, V. N, A, E, V is basically the same as before. So you can cancel it out. You are left with I1 ratio I2, that is 2 I1. Oh, sorry, no. Whatever this is, 1 ratio 2. So that would be I1 over I2, 1 over 2. So the second one would be 2 times by I1, which is 2I, 32C. An electric current is formed by moving charge carriers. What is not a possible charge on a charge carrier? So remember, charge is quantized, which means any charge is an integer multiple of fundamental charge, which is 1.6 10 raised to power minus coulombs. So if we divide these values by 1.6, 1.6, 1.6, 1.6, and if we are getting an integer, that would be impossible. So remember this. 32 is divisible by 1.6 or 16, so this would be correct. This is also correct. This is also correct because 48 is divisible by 16. This would be the only incorrect. So just a simple math, we can do 2.4 divided by 1.6. Powers at 10 raised to the power 19, 10 raised to the power 19. You are getting fractional value, so obviously the free electrons cannot be fractional in number. Which description of Kirchhoff's first law is correct? It considers the current at a junction in a circuit and is a consequence of conservation of charge. That is correct, but let's see the other one. It considers the current at a junction as a consequence of conservation of energy. No. No electromotive forces and potential differences. No. So it considers the currents at the junction, currents coming in, currents coming out, and it is the consequence of conservation of charge. Yes, so A is the right answer. Two resistors of resistances R and R are connected in parallel. The value of R is less than that of capital R. Okay, which statement about the combined resistance of the two resistors is correct? This is 10, this is 100. We don't care how much less it is. So effective resistance formula would become R times by R over R plus R. So this is 10 times by 100. This is 10 plus 100. So this would be 1000 divided by 110. Cancel, cancel. So 100 divided by 1. Oh, sorry, no. So as you can see, this is 9.01 roughly. So this is less than the smaller one. So it is less than R. So simple test to check this out. The diagram shows 4 identical resistors connected in a circuit. Which resistor dissipates the most power? Right. So which resistor dissipates the more power would be governed by I squared R. If the resistances are the same, the one which has the most current flowing through it would be the correct answer. So do we need to solve it? No, no, no. It's straightforward because the currents that are flowing through A are divided in these two branches. So the current flowing through B and C would be the same. And if these are identical, they would be dissipating the same amount of power. This would be dissipating twice that amount of B and C each, but still less than A, because A would be this, the current flowing through A would be the sum of current flowing through IB, ID. So the A is the correct answer. Nuclide X with proton number Z undergoes beta positive decay to form a nuclide Y. The decay may be represented by the equation, what is the proton number Y, and which particle is represented by symbol W. Okay, so remember this. When there is a beta positive decay, a proton decays into a neutron, beta positive decay, and a neutrino. Okay, so this is something you have to remember. So proton number decreases by 1. So proton number decreases by 1, and this is going to be neutrino, so this is B. Which fundamental particles form a hadron? This is very simple. Quarks combine to form hadron. And also, only quarks and leptons are the fundamental particles. Photons are not categorized the same way. The unstable nuclide 218X84 decays through a sequence of emissions of alpha and beta negative particles to form the stable nuclide. This, okay. So remember, beta negative, it raises the proton number. So in this case, neutron decays into a proton, beta negative, and an antineutrino. So proton number increases by 1 because of that. So, right, we need to see first off alpha. Okay, so there's an alpha also. So in alpha, we know mass number decreases by 4. Atomic number, or the proton number, reduces by 2. So, right, we need to see in beta decay there is no change in the mass number. So 218 minus 210 divided by 4. This is going to be just simply 8 divided by 4, so 2. So there's going to be 2 alpha particles. But how do they affect 2 alpha particles affect the beta? So proton number would decrease by -2. So that means -4. So this would become Z minus 4. Okay, so that would mean that 84 minus 4 would be 80. So we need to go to 83, so that means we need to increase it by 3. So 3 is represented by 3 beta negative particles. So 2 alpha and 3 beta negative particles. Simple math over here, simple algebra, nothing more. Which statement about the radioactive decay is correct? Neutrinos are always emitted during alpha decay. No. Alpha particles are emitted with radioactive sample have a continuous range of kinetic energies. No, they have a discrete set of values. Beta negative particles have a continuous range of kinetic energies. That's because of the sharing with the antineutrinos. And that's it. 40 questions done. So before we go, check out the grade booster pack that we are sharing in the link below. So this is available on Patreon. You can buy that. So let me show you what it contains. It contains AS definitions and formulas. So everything we have been doing in paper 1, including the reasonable estimates, definitions, formulae, are in this document, but for the rest, this is paper 2 AS frequently examined theory questions. This is the derivations. This is the A2 definitions and formulae. This is the derivations for A2. We did a lot of derivations in paper 4. This is the frequently examined questions for A2. As you can see, I think I wanted to show you the syllabus on the left side. So all the questions that are present over here, that means that it's due to the syllabus. So no question is out of place over here. And then we have the graphs. We all struggle with the graphs of fields, electric potential versus electric field, gravitational field versus gravitational potential. And then we have the planning question. This is the checklist, important items to remember. And then you have some worked examples. Hopefully, after January, we will roll a new version of the Grade Booster Pack, which would be again available on the Patreon. So if you buy this now, you will get a free upgrade when we roll it out. All right, so see you in the next video. Bye-bye.